Alrighty, we did not yet discuss how to find x-intercepts. So let's look at that for a bit. We know how to find the vertex with that negative b over 2a. We know how to find the y-intercept with f of 0. We can find a third point using the symmetry with the y-intercept in most cases. But we haven't said anything yet about x-intercepts and how to find those. So here's that same old example, number 14. We recall that the vertex is at 2, negative 11, and these points are 0, 1, and 4, 1. So the x-intercepts must be a little bit inside 0 and 4 on the x-axis. But where? Well, these are places where x is something or other and y is 0 before we let x be equal to 0. Now we're letting y be equal to 0, and then we need to solve this for x. So we add 11 to both sides, divide by 3, take the square root. It's gotten us this far. Now observe that this value inside the radical is almost 4. So the square root of that is almost 2. That looks good because we need a distance that is almost 2 right here between the axis and the x-intercept. Okay, so now we got a breakout of that absolute value. And when we do, we get plus or minus on the other side. And add 2 to the other side, and then we get 2 solutions, not just 1, 2. That's good because we need 2. Plus or minus. I wonder if some of this looks familiar. Okay, well, an equation with x-intercepts, I said earlier that there were 3 equations for every quadratic. There's the general form. There's the standard form, which is explicit about the vertex, and at the same time about the maximum or minimum of the function. And then there's this one. So this is one that we see very often when we factor a quadratic. We haven't even factored a thing yet. We get x minus this and x minus that. And if the value a was something other than 1, then we'll see that there too. And what we have here, these are solutions of the equation when we have 0 on one side. These are also known as roots of that solution, and they are the zeros of the graph. Looking back here, the zeros of the graph are the places where x is equal to whatever it is, and y is equal to 0. Those are very important in calculus. Oh, look. Solutions of this equation, this quadratic equation, it's the quadratic formula, which we all need to know by heart. Let's see, I already said that. Okay. So, we know that this, which looks like most of the general form of the quadratic function, except it has a 0 here, so it's an equation rather than a function. If this is true, then this is true, that x is equal to this part. So here we have both the vertex and the axis of symmetry. That did look a bit familiar. And here we have how far to the left or right of the axis of symmetry we need to go to get to the x-intercept. So what could go wrong with that? Well, let's see. What if a were equal to 0? But a is not equal to 0. We are not going to hear the denominator alarm, because we said up front on the very first slide that a is not allowed to be equal to 0. Otherwise, it would be a linear equation, and we wouldn't be here at all. So, there is also the square root alarm sounding right here. Now, if this is a positive number, then the stuff, when we get the square root of the stuff inside, we get a positive number. If it's 0, we get a 0. If it's negative, we don't get anything in the reals, we get complex numbers. We'll have 2 complex solutions. Now, I'm afraid I've run out of time to work on this video. These are examples that I will show in class. We will discuss the determinant briefly and a couple of applications. So, I look forward to seeing you soon.